This is 4.1.1 probability. So we are going to be talking about probability. There was statistics and now this is probability. So probability is the likelihood of an event that will occur. So how likely will you roll a dice? How likely will you spin this? And even weather in of itself, what's the probability it's snowing today or raining or having a nice warm day? Those are all based off of probability. So, determining probability. First, there are three different ways of determining probability. There's the empirical way, which is experimental and look at the observations. The theoretical, what is the actual theoretical possibilities? If I flip a coin, it's going to be 50%. And then subjective is I think that. It's an assumption. So the probability components you can do is get it through experiments. You can talk about sample space or a set of all the possible outcomes, the event, which is a subset of the sample space, and the outcome or sample point, the result of the experiment. So you have the experiment itself, what are the different outcomes that are possible, the event that happens, and then the actual event. So we'll talk about this in a coin flip. So if you flip a coin, that's your experiment. The sample space is there's two possible type possibilities, heads or tails. The event is it lands on its head. The outcome is the actual coin on its head. So the probability is a way to communicate what we think or could occur. Now we usually express those in fractions, percents, decimals, odds, but they're usually always numbers between 0 to 1. So total probability of all possible events occurring will total up to 1. So again, it's a fraction number. So the relative frequency of something occurring is the number of events that will occur total divided by the total number of events that can possibly. This will give us a fraction, a percent, decimals, odds. Again, those are all the different things. So what is the probability of tossing a coin landing on heads? Well, we look at our probability tree and we see it can either land on heads or tails. So how many possible outcomes can you have? Well, there's two possibilities with one desired outcome. So it becomes 1/2 or 0.5 or 50%. So what's the probability of landing on tails? Again, 50%. Now, what is the probability of tossing a coin twice and it landing on its head both times? Now, it's a little more complicated. So this is where you're going to break out that probability tree and make that probability tree a little bit bigger. So our first one, either head or tails. Then the second coin flip, heads or tails. Then we look at which are the desirable incomes. Which ones are going to land twice with their heads? Well, this is heads, heads, and that's it. So there's only one possibility. Out of how many possible tosses? 4. So you have 1/4, 0.25 or 25%. Now what is the probability of tossing a coin 3 times and it landing heads up exactly 2 times? Well, again, you're going to do this probability tree. And again, you notice how it's going to be a little more complicated. And so we're going to look at the desired outcomes. How many desired outcomes do we want? Well, having 2 heads exactly is heads, heads, tails, heads, tails, heads, tails, heads, heads, and that's it. So we have our 3 different possibilities. How many possibilities? We look at how many total number of throws we had, which is 8. So that's 3/8 or 0.375 or 37.5% chance. Now each trial has only 2 possible outcomes, yes, no, on, off. That means it's binomial. So like tossing a coin, the trial outcomes are independent. The first coin does not affect the future tosses. And so we can use, instead of having to do this whole tree thing for indefinite numbers, we can use this equation. This equation looks ugly, but it is not that bad. You will have to use a calculator for it, but this can give you all of what we did without having to draw out the possibilities. So first off, factorial is the explanation. That is the product of all integers less than or then it is equal. So you just add up. So n factorial, so 3 factorial would be 3 plus 2 plus 1. Or sorry, 3 times 2 times 1. And then, so we have P is your probability. X is the number of times for the specific outcome within the n trials. So n of the trial, n represents the number of trials. P is the probability of success on the first trial. Q is the probability of failure. And again, the factorial. So you just plug in the numbers, you find what the numbers are, plug it in, and then chug it out into your calculator. So again, we can do the same thing, but we can put it in. N factorial, 3 times 2 times 1. What's the probability of flipping on the first? It's 0.5 times X, which was 2. Q is what's the probability of failure? Again, it's 50%. N, which is 2, minus 1, which gives us 1, all divided by X, the probability of happening, 2 times 1, that's 2 factorial, times n minus x, 1 factorial, 1 again. So we plug that in and we get that same number. So what I want you to do is kind of look at these numbers and see what they are. Try to figure out how they came to be. Now, the law of large numbers says that as we get more and more numbers, the closer and closer you are to the probability. If you toss a single coin 5 times, you might get heads, tails, heads, heads, tails, which actually gives you 60%. But as you get more possibilities, let's say 500, you're going to actually get a probability of closer to 50%, which is the theoretical probability. Now we're going to talk about AND. Just like Boolean logic, ANDs and ORs actually have a mathematical thing. So if you have something, what is the probability of this occurring and that occurring? You take the two probabilities and multiply them together. So what's the probability of rolling 4 on a single dice? It's 1/6. What's the probability of rolling 1? Again, it's 1/6. What's the probability of rolling a 4 and then a 1 sequentially? Well, you have to multiply those, which gives you 136 or 0.02 or 2%. OR is additional, so you take the two probabilities and add them. So what's the probability of rolling a 4? 1/6. A 1, 1/6. What's the probability of rolling a 4 or a 1? Well, you add those probabilities together, 33%. A NOT is then subtractive. So it's a 1 minus the probability of it occurring. So what's the probability of not rolling a 1? Well, it's 1 minus the probability of rolling 1. So 1 minus 1/6 or 5/6, 83%. Probability of 2 cards. So how many cards? 52. How many aces are in the deck? Well, there's 4. How many face cards are there in the deck? Well, we'd have to think it up. There's the king, queen, jack. So that's 3. And there's 4 suits, so that's 12 total. How many 10s are in the deck? 4 again. So what is the probability that the first card in any is an ace, the second card is a face card or a 10? So we take the probability of the first card being an ace, 7.69. Since the first card was not a face card, it is probability the second card is also a face card. So since the first card was not a 10, what is the probability the second card then is a 10? And that adds it up to, we got our 23%, 7.8. Notice that we have subtracted that first card because we've already picked it out. So that's going to lower our numbers 1. So then we take our probabilities. Again, our first probability is an and then our second one is or. Then our second one is an OR, so you add them up and add that into your calculator. It gives us 2.4%. So if the first card is an ace, what is the probability the second card is a face card or a 10? 31.37%. Alright, conditional probability. Probability of event of E given A. An example, one card is drawn from a shuffled deck. The probability is equal to a queen. So the probability of a queen happening is 4 out of 52 or 1 at 13th. However, if you already know that it is a face card, then decreases the probability from 4 to 12, 4/12 or 1/3. The probability of two events occurring, again, is multiplicative. So, now we're going to go into Bayes' theorem. What I would recommend is pausing here, go to this website. You might have to look up Veritasium and watch this video. He explains it a lot better and a lot and more concise than I can. So, Bayes' theorem is this big ugly equation here, and it's calculating what is the conditional probability based on all the ways the conditions might have occurred. So the probability of something occurring giving A, given we already know the condition of E. So here it is. An LCD screen company has, for a large cell phone manufacturing company, are outsourced to 3 different vendors, vendor A, B, and C. Supply you with 60%, 30%, and 10% of the required LCD screen components. The quality control experts have determined that 7% from vendor A, 1.4 vendor B, and 1.9 vendor C components are defective. So, if the cell phone was chosen at random and the LCD screen was determined to be defective, what is the probability that LCD screen was produced by vendor A? Well, this is where it gets a little crazy. We use the P to denote the probability, D's for the defectives, and ABC denotes the vendors. So what's the probability of A being defective? Well, we plug it in. What's the probability of being A? 60%, B 30%, 10%. What's our conditions? Well, what's the probability of D, defective of A? Well, that was given us to our problem. And we get our 7%, 1.4, and 1.9. So then we plug in our numbers. The probability of being A times the probability of the defective of A, all divided by probability of A times the probability of its being defective of A, plus the probability of B, defective of B, plus of C times the defective of C. Then we divide that out and put it into our calculator. So we plug that in, and it gives us 40%. So 40% chance that the company A was responsible for that defective screen. So we can do this for B or C. What I want you to do is try to do it for B and C. So if you have any questions, again, ask your teacher.